Hello. 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 Hello, Ashley. Thank you. Hello. I appreciate that. Okay. Hello. Hello. Good afternoon, Montserrat. Okay, here we go. Good. Hello, Gianna. Hello, Ashley. Good afternoon, Montserrat. Top of the afternoon, Abdel. Whew. Wasn't going to be the same with that. Hi, Sumaya. Hi, Sarah. Okay. Hello. All right. Hold on. The board is giving me problems as usual. Okay. Hello. I think the board is coming in a minute. Okay. Hello. Oh, sorry. Did I say Liana? Good afternoon. And hello, Brian. Hello, Tobias. I love those cards. Okay. Hold on. Good afternoon, Jasmine. Thank you. Okay. Oh, and there's Alejandro. Sorry. And good afternoon, Kay. Okay. Okay. My board just stopped again. Oh my God. Sorry. I don't know why. Okay. So here's good afternoon, all my health. Thank you for saying hello, Alejandro. Okay. Hello, my board, which is where is my board? Okay. Okay. So I missed you on Monday. I missed you on Monday. I appreciate all your flexibility and patience. Many of you have gotten your exam back. Many of you still have not. I'm very aware of that. I'm very embarrassed by that. They're just coming one at a time. I don't know why they're taking me. I don't know why they're taking me so long. Many of you have them. Many of you don't. There's no rhyme or reason to who has them and who doesn't. They're just coming. That's all I'm doing right now is these exams. They'll just keep coming until they're all back. I really appreciate how patient you're being. I know it's really annoying. You're still not having it, no new homework like ever, really. I mean, the only homework anybody should do between now and the end of the semester is anything that they want to do that that they hadn't done before that they want to still get more points on. I'll talk about that in a minute. Oh, there goes my board again. I will just keep sending these exams back as I continue to finish them. I will talk about them a little bit right now. So some of you, some of you in the room have gotten yours back. Some of you have not. I want to say some things anyway about them. It'll apply to all of you, I hope, I think. Hello, people who just walked in. Okay. So first of all, and this also applies to both sections, the exams I've seen, I can tell you, it is clear that you're doing work in this class. It is clear that many of you are very talented, very smart people who are working very hard, like almost anybody who's in the room right now who's listening to me. You are working hard. You are smart people. You have learned some physics. There are exams that I looked at where where I was seeing how strong you are, how strong your work is, really. And when I got to the end and I saw the number, in many of your cases, I'm talking like, excuse me. Okay. And I think many of you know, I'm talking to many of you, and I think some of you know who you are that I'm about to say this to. At the end of some of your exams, I got to the number and I thought, uh-oh, he or she is going to be worried about this number. He or she is going to be more worried about this than I am for him or for her. There were many cases, and I want to make this clear to all of you, that I saw some exams where I saw the strength, and I know the student, and I know many of you. I'm increasingly knowing you, and I know what good students you are, and I know how concerned you are about grades and stuff like that. And I can tell that there were some numbers in this room where you would think, oh my God, am I in trouble in this class? Or you might think, oh my God, I hate Yaverbaum, like I want to bomb his like house now, or whatever, like both of which would be fair. I want to tell you, I want to remind you of a number of things, such as the grading system. I want to assure many of you that the number that you got on that document is not the number that you're ending up with in this class. Like, I know this from many, many years of experience and from this grading system. I'm going to put this in more perspective. And again, I know some of you don't know what I'm talking about because some of you haven't gotten your exams back, but just take this as an advanced piece of information. I want you to put the number in context when you see the number. And I want you to know that I'm putting the number in context. None of you is just a number. And certainly none of you is just the number that you got on that piece of paper. Let me be more clear for a minute. And again, and I sound intense right now because all of this stuff always freaks me out. I mean, it takes me always way too long to grade these things. And it causes I know how invested all of you are in your present and in your future. Believe me, I know. And I know how hard a lot of you are working. So let me say a couple of things, especially those of you who've gotten the number back, but even to those of you who are building anxiety because you haven't seen the number yet. Let me start by saying this. For example, if you got in the, oh my God, wait, there's more people coming. Pardon me for a second. Well, let me start by saying this. The way the grade is calculated for the end of the semester, please remember, and no one really it's easier to understand this and appreciate it once you've been through the whole thing and you're in physics 204, because the grading system works the same way in physics 204. And by that time, people usually sort of believe this more or can see this more. But what happens at the end of the semester is you have your midterm grade, your midterm exam grade, you have your final exam grade, you have your final lab grade. Okay, those three get averaged together, those make an average, yes. But then added to that average is a huge number of points that comes from all the homeworks you did, all the game turns you did, all the game things you did, any extra points you ever got, including many things you turned in that you still haven't even seen the points for, but all do get added in and put into your final average at the end. All these, and by the way, which also you could still turn in now till that last day of classes, anything that you find that you haven't turned in yet, any old homework or any game thing like show video or show avatar or anything like that. The only exception is like the nightly game turns, like it doesn't make sense to go retro, do a bunch of those. That doesn't make, but anything else that you find, all those things are worth points, right? Just to remind you, all those points accumulate up into one big pile. At the end of the semester, that pile is divided by one scaling factor number that is the same number for all students. Let me give you a quick example again, and please bear with me. Like you've heard this before, but it always means more to people to understand after they get an exam or after they've taken an exam. So let's say at the end of the semester, let's say you have 150 points accumulated from all of your homeworks and all of your game turns and all of that, which again, by the way, you can still turn those things in until the last day of classes. So say you have 150 points accumulated from all that stuff. At the end of the semester, I divide the 150 points by some number that I can't know now, but it will be the same for every single student. I promise you that. Say the number is 15, for example. So you have 150 points. It gets divided by 15. Like you might have 150 points. Your neighbor might have 200 points. Your other neighbor might have 100 points. But all of your whatever you all have gets divided by 15. So say you had 150 homework points. It gets divided by 15. That makes 10. 10 points is then added to, like literal 10 points is added to the average of your midterm, your final, and your lab grade. So if your average was like an 80, now you have a 90, okay? Then potentially you might, in fact, also get 1 point of class participation. Like any of you who've ever like talked in this Zoom or ever put anything in the chat in this Zoom or anything like that, you'll probably get 1 point of class participation. Quite frank, I'll explain that even more in a minute if you want me to. But so you get those homework points, plus you get a point for class participation. That gets added to your exam average. So if your exam average was like an 80, you'll now have a 91. That's fundamentally different, right? That's the difference between a B minus and an A minus, as you know. And that's not an accident. B, it's not a gift. It's because of all the work you do in the class. C, it's not an it is a realistic example. Like it's just an example. It's just an example, but it's pretty realistic. Like most people in the room, most of you who are listening to me right now, the amount of points that you're going to get at the end from all the homework you've done and all the participation you've done, it's usually on average around 10 or 11 or 12 points or something like that. It's designed, the system is designed to make like a solid letter grade difference in your overall performance, because most of the work you're doing is every day. It's not just in the couple of times that you take an exam. And I know that, and you know that. So none of this is a gift or anything like that, but it's to recognize that you do a lot of work, even just tuning in, you do a lot of work that's not just on those exam days. So first thing I'm trying to say is whatever you got on this exam, you should assume that if you trend and do the exact same thing on your final, you know, you add a bunch to that in your mind, and remember that you also have a lab component of this course before you start thinking that that number on the exam is literally your letter grade in January. Okay, that's number one. Number two, to put it in perspective a little bit more, I could tell you right now. Sorry. Oh, okay, got it. Got it. Okay, thank you. Thank you. Awesome. Got it. Thank you. Number two, or that was number two. Number three, again, and I'm speaking to all of you, okay? I am, well, anyway, number two, most people did not get in the 90s on this exam. There's still exams to come, but most people generally don't get in the 90s on the first midterm of Physics 203. 90 is a fairly unrealistic, fairly uncommon score, but a lot of people get A's in the class. Okay, so like so the average so far, I mean, the average on this exam was like less than 80, I think. So already I can just tell you, even if you're used to getting 90s, or you like getting 90s, or you think nothing less than a 90 will satisfy or something like that, I can tell you right now that if you got anywhere in the 80s on this exam, and I know some people didn't, and that's also fine, but if you got anywhere in the 80s on this exam, oh, you should definitely already be thinking you're fine. Like if you do the same thing on the final or better, you are trending for an A in the class, just to put that in perspective. That does not, now, again, let me say quickly before anybody misinterprets what I'm saying, I am not saying that if you didn't get in the 80s on this exam, then you're not getting an A in the class. I'm not saying that. If you were even in the 70s in this exam, you have not sealed your future in any horrible way at all. Like really, if you're in the 70s in this exam, you're like, there's no crisis. There's no crisis. If you got lower than the 70s, it's still not a catastrophe, but sure, if it's lower than the 70s, we might want to talk just to see what's going on, or to straighten things out, or to give you an opportunity to figure out some things better to do for the final, because there still is a final, and you know, sure, we'd like to do better on that. But there almost nobody who's in the room right now. In fact, I can even tell you for a fact, and I'm not mentioning there or anything like that, there were a couple exams where the numbers were like in the 60s or something like that, but they were gorgeous exams. I don't just mean gorgeous like good looking. I mean like, whoa, was clear effort and clear thought and clear clarity and comprehensiveness and thoroughness. There were a couple exams where where like the overall product was astounding, but yes, there were a lot of mistakes and stuff like that where, okay, so it counted against the number. But I just want everybody in this room to know that I'm seeing a bigger picture than just some number, and I want you to do the same. Even if your number might have been unsatisfying to you, if I wrote comments on the exam like, oh, this is beautiful, or wow, this is or especially if I put like plus here or plus there or something, that means I am also seeing and recognizing what you are doing, and it all gets taken into account in the end. It does. So okay. Also, and there's still time for you to look back and look at other homeworks that you could still hand in, or ways that you could catch up. There's going to be huge compassion and understanding for you. I'm also asking for in both directions. Clearly, I'm not perfect. Clearly, I still have to get far from it. There's still people waiting for their exams. I know what anxiety that causes. That's taken into account. It might, believe me, I recognize that that doesn't help your performance. So I that's taken into account. So, and I don't want to spend this whole class, but I think you're a very good group. And I know that. And I think I know how invested you all are and how worried often you can be. I'm just here to say, please know that I see that, and and we're all on the same team looking for performance. And I'm going to get more concrete as I go here. And again, I know this is like annoying to some. This is like super annoying to hear if you don't even know what your score is yet. But just take this as the context. Oh, okay, wait. So I'm looking at the chat. But take this as a context of how to read the number when you get the number. Okay, hello, wait. Oh, okay, wait. Oh yeah, no, that's fine. I'm seeing some things in the direct chat. So some people in the direct chat are like, apologizing to little things to me, which I totally appreciate. But look, also take this as my way of apologizing to you. We're all in this together. It is tough times all around in all ways. These are tough times, and you're in a tough major. And I will never forget how tough your major is. Believe me, I will always have one of the reasons I speak this way is I know what a tough major this is. I'm in awe of you guys. I'm honored and privileged to be teaching in this major. By definition, to be in this major means I'm working with students who are really intense and who are asked a lot of the time. And I can't keep up with you half the time. And I know that. So it's the compassionate, I'm asking to go both ways. And I'm saying it does come out in the wash. It's recognized. Anyway, so no, I appreciate some of the apologies you guys are giving me in the direct chat, but take this as my apology to you. Yeah. So, okay. No, this is a good question in the direct chat too. Is there an average? Yeah. So far. Yeah. So the average, I think the average so far on this midterm exam, I do believe the average so far is a 71, just to be honest, because someone's asking that direct chat, totally fair question. Okay. So, and this is what that means to me. So far, the average is 71. Obviously, it'll change when you get more data back. And again, I know it's stressful to be sitting here listening to me when you don't even have a number yet. The average so far is a 71. What that means to me so far is when you get your number back, if it's over a 71 or significantly, then you definitely should just right away breathe out and be like, okay, I'm okay, I'm in. But it also means even if it's a little lower than a 71, understand that. Like if you see a 67, if you get back a 67 or something, just an example, don't think that's a D. I'm definitely saying that. Even if you got a 60 back, don't think if you got a 60 back, and I am talking to some of you in particular, I know who I'm talking to, and believe me, I also know. If you got a 60 back, do not be sitting there thinking, holy crap, I have an F in this class or a D minus. You might want to think, okay, like let me talk to Yaverbaum when we each have a moment so we can straighten out what I can do better for the final. Sure. But just understand that just means, yes, you did a little worse, a little less than the average. So there's something where we could improve something. But don't think that these numbers are coming from God or going straight to God. There's a 60 on this exam does not mean an F in this course. It means, okay, let's talk about this exam. Okay, so yes, but sorry, to answer the person in the direct chat, totally fair question. So far, the average is a 71. So you can measure yourself against that to whatever. Yeah, okay. And just please remember again, now I'm going to be more concrete in a second. There's a reason I'm saying all this. Partly I'm saying all this because there's enough numbers that have come back already that I know how some of you feel. Also, I've gotten some feedback from some of you already. And believe me, anything on your exam that you don't understand where I took off points or why, of course I will talk to you. And it doesn't have to be tonight for it to change. Do I ever change people's scores after I talk to them? Do I ever admit that I've made a mistake or something? Sure, I do. Yes, I do. Sometimes it turns out I didn't make a mistake and I have to explain something to the student, but I'm always open to that conversation, and it doesn't have to happen tonight for the number to change. If there's a mistake that I made, of course I will correct it, because one of the larger themes in this whole thing that I just want to assure you, and I know it's hard to believe in the science majors thing, the one thing I just want to assure you is you are not competing with one another or with me for your A. Yes, you have to work hard for it. Yes, it's not a gift. And yes, some people don't get A's, which means, yes, if you do get an A, you should be proud of yourself and it really means something and it wasn't automatic. Yes, you have to work for it, but you're not fighting your colleagues or me for it, which means literally this. It means there's not a limited number of A's to receive in this class. Like I'm just as happy for you to legitimately get an A as you are. That's an important thing to remember as we go through. It doesn't mean you automatically get it, but it means I promise you, you shouldn't be like, don't think that when someone else gets a point that comes out of your bank, or don't think that that if you come to me with a question like, could you explain why I lost points in this question? Don't come to me thinking that you have to like win against me to get that point back. I want to see that I made a mistake just as much as you. I mean, if I did make a mistake, right? Or I want you to see what the error is that you made so we can straighten it out for the final exam. But we're okay. I like that's part of, so and put one final way of all this. I want you to earn good grades. I don't want it to be a cheat or a gift, but anyway, we can get there. I want to get there. So another way to put all this is I'm here to judge if a grade, there goes my board, but if a grade is a judgment, which I wish it weren't, but if in the end, somehow a final grade is kind of a judgment somehow, I'm here to tell you that my system is designed, or I try to design a system so that the final judgment that you receive at the end is a judgment of the best foot that I ever saw you put forward, not your everyday foot, not your average foot, not your weakest foot. If you ever show me something really strong, then that lifts, that gives me something to work with. As long as each of you gives me something to work with, we work with that to channel it into the best possible grade you can get. Like, again, I just want to be specific. I'm just looking to see who's in the room. I'm looking to see who I'm talking to. Yeah, like, again, I just want to say there were a couple there. I know there was like at least 3 exams I can visualize in my mind right now where the exam itself impressed me more than the number might indicate to you. And you will be more scared by the number than I want you to be. And I want you to know in at least 3 of your cases, what you gave me in the exam was a reason to root for you as much as you're rooting for yourself. So let's take that and convert it into whatever our next steps are, even if improvement is necessary in certain areas for some of you. Okay, but just understand the minute anybody gives me something, some reason, and most of you have, whether it's like just freaking awesome presentation of the material or awesome participation in the Zoom room or awesome homework, like as long as you give me something where it's like, now I'm rooting for that person, then we work together and get you to that A or that B, which is still fine in science, believe me, or whatever. Okay, now, having said all that, to be more concrete, and I know I keep losing my board, but to be more concrete, and you may have seen this in, someone's here, sorry. You might have seen this in Google Classroom a few minutes ago. There's no new, okay, sorry. So there's no new homework really that's going to happen at all till the end of the semester. We're just going to try to catch up with ourselves to the end of the semester. You're going to try to catch up with any opportunities you see to get more points. You're going to try to turn them in. I'm going to keep on just trying to catch up and return your exams, right? Blah, blah, blah. Like anything from here on in is any optional opportunity to get more points until we get to the final exam, which is during final week. But you might have noticed in Google Classroom, I'm about to turn the board back on and go back to the new material that we're in the middle of. And you're going to see that the first page of the board, as soon as I turn it on, is a problem that I'm going to try to teach you and help you solve most of today. There's a new problem. And just like same kind of in the spirit of the exam, I'm giving you a week till midnight, a week from today. If you do a nice presentation of the solution of this problem that I'll put on the board, and you turn it into the portal that's marked like extra points on exam, as long as you do a nice, thorough, multi-step presentation of this, it's optional, but as long as if you choose to do it, then I'll give you up to 8 points back on your actual exam score, not just 8 points of just general homework points, but literally back. In other words, it's 8 more points you can get on the exam. Okay. And that's partly my way of saying to you, believe me, I see the work that you put in the exam. It's also partly an acknowledgement that I don't think it helps that I'm taking this long to grade them. So I'm giving you more points than I'm sort of normally would on a thing like this. And maybe I'll even increase it like when my head is clear once I've gotten all the exams back. But oh yeah, okay, the board. So here comes the board. Sorry. Yes, you're right. The board keeps, but here, okay. But anyway, what's about to be on the board is, so it's for 8 points on your exam. Again, that can, that'll change the whole letter grade right there. Okay, here it comes, I think. Here it comes, okay. But thank you for telling me. Okay, here, okay, so that's here. Okay, here's the problem. Here's the problem. Okay, and I'm going to spend the rest of this. I know I'm talking a lot, and by the way, also I know I sound tense. I'm tense about me, about that I still want to get these numbers back to you, and I'm tense because exams always make me tense. But don't misunderstand my tone. I'm not angry at any of you, not at all. I'm worried for you, but only for your, but I'm not worried about you, if that makes sense. Okay. Exams always just get in the way of, okay. So anyway, so what's on the board here, and please do copy it down or whatever. Okay. What's on the board, again, this is problems called horizontal haul, as in haul. And I'm changing the view on the screen now. So from here on in, please, please put questions or anything that's unclear or any complaints or concerns in the chat. But so this problem is called horizontal haul. The setup, and this is the only copy of it, though there isn't like a separate copy in Google Classroom, so you do have to be paying attention. So the situation is we got a block on a horizontal lab table. We've got a block on a horizontal lab table. Here, I'll even just maybe. Okay, we've got a block on a horizontal lab table. There's a string with tension in the string pulling the block at an angle. So someone's like pulling the block along the horizontal table. They're pulling at an angle theta, right? But they're pulling at an angle just because it's easier to pull that way. But the block, as the wind sketches are meant to indicate, the block just accelerates horizontally along this horizontal table. The table is rough. It has friction. That's the main thing I'm going to try to explain today in lecture. I'll explain how to deal with that. But the table is rough, so it has a coefficient of friction known as mu. And the value of mu in this case happens to be 0.3. That, I know you've dealt with that in the lab, but I'm going to explain that like in a minute. But so the setup is that there's this block on a horizontal table. It's being pulled at an angle with some force of tension by a string. And so the block accelerates to the right horizontally along the table. And the ultimate goal of the whole thing, the ultimate goal is solve for the horizontal acceleration of the block. Now, I'm going to walk you through this in a moment, or as much as I can. And you're welcome to work with others and blah, blah, blah. And you have a week, but what you're ultimately going to do is step by step, a full solution, solving for the acceleration of this block. Again, it's not required homework. You don't have to do this at all. But if you do it and you do it nicely, even if you make some mistakes or this or that, but if you do it nicely and comprehensively, then you'll get 8 points back on your exam. Oh, and so I'm going to start explaining in 1 second. Oh, I'm just looking at the time. All right, we've got. Oh, I'll have time to do this. Okay. And also I did fully walk. Anyway, I will explain it in a second. One other just piece of advice too. Again, I think people worked very hard on the exam. I think I think people showed a lot of integrity. I think there was like a lot less cheating than usually goes on too, which is to your credit. Sounds like a weird thing to say, but one piece of advice that would make it a little, I think would help many of you and would definitely help me grade your exams is spread out your work a lot more. All of you could, most of you could really stand to give yourself a lot more space. However you're writing these things out, give yourself a lot more space, take a lot more pages. First of all, definitely start a new page for every new problem, for sure. Please do that. That's just a good practice in general. Second of all, if you're on lined paper, definitely skip lines. If you're not on lined paper, spread out, give yourself way more space than you think you need and make your handwriting way bigger than you think it needs to be. You will find actually that actually unclutters your mind a lot more. It actually makes it easier to think a lot more, just like having more time to think relaxes your thinking. Having more space to think really helps. And it also makes it a lot easier for me to follow and grade efficiently. So just maybe use this as an opportunity to practice that. Really, almost all of you could benefit from spreading out your work a lot more. Okay, that said, here's the problem again, and put in the chat if you don't, this is the problem. It's not going to be printed anywhere else. This is the situation. We're solving for the acceleration, the horizontal acceleration of the block given the situation. Now, in order to solve this, we're going to follow our customary Newton's laws procedures. I'm going to make one correction here. I'll read my handwriting out in a second. Okay. The customary Newton's law procedure. I mean, we always have our 5-step method going on for all kinds of problems, but specifically how it gets applied to specifically Newton's law problems in order to solve for the acceleration in some complicated force situation like this. First, we draw a system schema. That's step number one. We draw a system schema to identify all the forces. Then we take all the lines from the system schema and turn each one of those lines into an arrow, a vector in a pure free body diagram. The pure free body diagram shows the directions and the comparative magnitudes of the forces acting on the object. Then we identify all the action-reaction pairs, the Newton's third law pairs, like in English, we list them out so that we can make sure we don't accidentally, good question. I think I changed it to a T, didn't I change it to, but P, okay, wait, good question, sorry. Where it, P, sorry. Oh, I see why you're saying that. I'm sorry. Good question. Hold on. Great question, both of you. Sorry, it's T. Sorry. Yeah, it says P. You're right. My mistake. Originally, I had a P as in pull, but now I realize it's more clear and straightforward for it to be T as in tension. Sorry. So it's the same. The T and the. Thank you for noticing that. Yeah. No. Good question. Thank you for paying attention like that. Really, all three of you, Alejandro, Brian, and Tobias. Thank you. Yes. So my bad. So we're pulling up the block at some angle with a rope, and there's tension in the rope, and the tension equals 200 newtons. Yeah, my bad. Thank you. Okay. So the procedure is we draw a system schema, then we draw a pure free body diagram, then we're going to write out all the action-reaction pairs. Then we turn the free body diagram into a component free body diagram, and then we use those components to solve F net equals MA along each individual axis. That is the procedure, and that we're about to follow. And that's what we will follow. But first, the one thing I want to teach you about, now you've been sort of expected to use this in lab, but we've never explicitly yet, or we haven't finished explicitly talking about friction and how it works in the lecture. So here we go. So because there is friction in this problem, and I'm partly using this problem as an excuse to teach friction and to teach angles. So let's investigate the nature of friction. Remember, we said when we were doing system schemas that whenever you have two rough surfaces pressing against each other, they actually generate two lines in a system schema. Whenever two surfaces push against each other, they actually create two forces at the same time. One force is the sort of obvious push that is perpendicular to the plane of contact. If my two hands are pressing against each other like this, the plane of contact is like that. My two hands press along an axis that is perpendicular to this plane. Perpendicular in math and science is called normal. I mean, the word normal in math and science just means literally perpendicular. So when two things press against each other, first of all, they exert forces perpendicular to the plane on which they're making contact. So we call that the normal force. But if the surfaces are rough, automatically for two rough surfaces to squeeze against this way means they will automatically start resisting motion along the axis parallel to the plane of contact. When you squeeze two things, it automatically makes it difficult to rub two things or to slide two things along each other. In fact, the harder you press two things, the harder it is to rub them against each other, because surfaces microscopically are like have nooks and crannies, ridges and valleys. So when you push two surfaces against each other, it's like pressing two combs against each other. The teeth of the combs get interlocked. So the harder you're squeezing the combs together, the harder it is to go like that. So every normal force brings with, assuming that surfaces are at all rough, a normal force will automatically bring with it a force parallel to the plane of contact, and we call that friction. Okay, so friction accompanies normal. They are two components of the same overall phenomenon, which is surfaces pressing against each other. If surfaces aren't pressing against each other, they won't rub against each other. So if the normal force is zero, the friction force is zero. As the normal force starts getting bigger and bigger, the friction force starts getting bigger and bigger. And in fact, it turns out that the frictional force is not only proportional to the normal force, but it's approximately directly proportional to the normal force. So if I were to make a graph, this is what's going on now in the blue here on the page. If I were to make a graph, if I were to graph frictional force as a function of normal force, I would actually get a straight line, pretty much, approximately. I would get a line, I would get a function of constant slope. For every 1 unit of normal force increased, I would get the same number of friction force units increased. And what are those units? They're newtons. Friction is a force, it's measured in newtons. Normal is a force, it's measured in newtons. Okay, so the slope of that graph would be constant. Slope E equals rise per run, like delta y over delta x. Only in this case, like y2 minus y1 over x2 minus x1. Only in this case, it's not y and x, it's f and n. So the slope of the friction per normal force graph, the slope is a constant. We call that constant mu, the lowercase Greek letter mu. That's the brown thing, okay? Mu is the constant of proportionality of friction to normal. In other words, so mu equals change in friction force per or divided by change in normal force. You know, switch both sides. I mean, multiply both sides by normal. And what we're ultimately saying is the friction force that is generated when two surfaces press against each other is mu times the normal. This is like saying y equals mx plus b, only b is 0. And m here, the slope, is mu. Now, mu is a dimensionless number. What I mean by that is mu is a ratio of newtons to newtons. So the newtons cancel out. It is a pure ratio. In fact, literally, it's a ratio, like it's a fraction. Mu is generally a number between 0 and 1. I mean, it's always greater than or equal to 0, and it's generally less than 1. So we call mu a coefficient. In fact, mu is the coefficient of friction. Coefficient generally means a fractional number that has no units. What does it measure? What does it indicate? Well, it indicates roughness. What I mean by that is this. Mu is the slope of the friction normal force graph. Mu is how much friction you get per each Newton of normal force. If mu is really high, that graph has a really steep slope. And if mu is really low, it has a really low slope. Why in one situation? So in one situation, I might press two things together and get a lot of friction. In another situation, let me say that again. In one situation, I might press one surface against each other, another, and get a small amount of rubbing or sliding resistance. In another situation, I might press one surface against another with the same amount of normal force, but get a lot of resistance or sliding friction. Why would I get more sliding friction per unit of normal force in one situation rather than another? I would if I had rougher surfaces involved. In other words, roughness is the determining factor as to how much friction you get per each unit of normal force. In other words, this equation in the middle of the page, F equals mu times the normal, what it's really saying is the amount of friction that you ever get on one surface from another comes from two factors being multiplied by each other. The two factors are the roughness of the surfaces and how hard they're squeezing against each other. If either one of those numbers is zero, you don't get any friction at all. If the surfaces are perfectly smooth, if they're perfectly like a cushion of air, like in an air hockey table, if it's perfect, and even that's not perfect, but if they're like super, super smooth and mu is like zero, no matter how hard you squeeze the two surfaces together, you'll get barely any frictional resistance. On the other hand, no matter how rough the surfaces are, they could be like rubber. But if you're not squeezing them together, if they're separated, you're not going to get any friction. So the more rough the surfaces are and the more you squeeze them together, the more friction you have. Literally, it's a multiplication. Mu, so how much friction force is there in any one surface from another? It's literally the normal force measured in newtons times this dimensionless number that ranges from 0 to 1. This dimensionless number that ranges from 0 to 1, this coefficient of friction, is really just a rating of roughness. Like an air hockey cushion has a roughness coefficient of nearly 0. Maybe ice, like fresh ice zambonied in a hockey rink, has like a mu of like 0.001 or something like that. Then maybe glass has a mu of like maybe 0.1, maybe then plastic or linoleum is like 0.2, and then like wood is like 0.5, and rubber would be like 0.9. So when you're given the mu, in this problem that we're about to analyze, you were given the mu, you often are given the mu, you're given a mu of 0.3, not 0.3 newtons, 0.3. Does that mean the friction force is 0.3 newtons? No, it means that 0.3 is how rough the surfaces are. When you multiply that by the normal force, we'll have the friction force. So in summary, what I just said, this is what this page says. It says, so the friction force exerted by one surface on another is determined by two factors. One, the roughness of materials, that's mu, and two, how hard the materials are pressing against each other, which is the normal force. Just note, and we're going to see this in the problem that we're about to do, and we have 30 minutes to do it. I mean, you understand what I'm saying? So friction force is mu times the normal. The normal is not a formula. Often people think there's some formula that they want to look up or they want to memorize to calculate the normal force. Sometimes, but that's not the case. You always have to freshly calculate the normal force in any given situation. Today is definitely an example of that. You can't walk into the situation and just know, aha, the normal force equals mg, or aha, the normal force equals mg times cosine of theta or something. That's a trap that people often fall into. Do not believe the hype. The normal force changes from situation to situation. Some situations there is no normal force and therefore there's no friction. But whatever the normal force is, you figure out from doing Newton's laws. And that's what we're going to do now. And you're going to see. Okay. But so the friction force, which we generally have to calculate in a problem, is mu, the friction coefficient, times the normal force. Okay, now let's see how that plays out in this situation that we have here. Yeah, okay, so let's apply this friction knowledge to the example of horizontal haul, the problem that you'll get extra credit for. All right, so the diagram, I'm going to go through this. I'm just going to do the solution now. Like you have the diagram, it's on the first page. The diagram is a box on a table. You're pulling the box up and to the right, and the table, and the box glides along. The mass is given, the angle is given, the tension is given, the mu is given. All right, so first what we always have to do is we draw a system schema of the box in question, the mass in question. So I drew a dotted circle around M for the mass of the box. I drew a dotted circle because that's the object of concern. I drew a circle for PE for planet Earth, because planet Earth is in every single situation. It's in every system schema. It's always pulling on our object. So I drew that first, I always do. Then after I draw planet Earth, I draw a solid circle for every object, for every and any object that is touching our mass in any way. Well, there's a string touching our object directly. So there's a string directly touching the object. It's pulling up on it. So I draw a solid circle representing that string, and I draw a line to the mass because the string is touching the mass. There might be somebody touching the string, holding the string, but I don't put them in the diagram because they're not touching the mass, right? The string is touching the mass. Okay, so I put the string in the system schema. Then I say that there's a table touching the mass, but I remember that the table is a surface that is pushing against the surface of the mass. So I follow that rule that whenever I have two surfaces pushing against each other, I always draw two lines in the system schema. So remember, every touch gets one line, like the string got a line, but the string is touching it once, so it got exactly one line. But then there's always the two exceptions. One is gravity gets a line, planet Earth gets a line, even though planet Earth is not touching the box, because that's just the way gravity works. And the table gets two lines because it's a surface pushing against the block. So that's my system schema. And the purpose of that system schema was to literally get the number of lines. Like I see there's 4 lines in my system schema. So now I know when I turn the page and draw a pure free body diagram, there are going to have to be exactly 4 arrows in that free body diagram, one for each of these lines. So I go to the pure free body diagram. Here comes the pure free body diagram. Each one of those lines becomes an arrow, and the arrow points in the direction that the force is actually being directed. So first I took that line that came from planet Earth. I know planet Earth is pulling my box down with a force of weight of mg, like m times 9.8 number. So I draw a down arrow indicating mg. It's in every single free body diagram. I always draw it first. It's always there, the down arrow that says mg. Then I noticed that the table is pushing up on the block. Like that was one of the 2 lines in my other diagram. One of those 2 lines is the force of the table pushing perpendicularly to the plane of contact between the table and the block. That's called the normal force. So I draw an up arrow indicating the normal force, the force that the table is exerting up on the block. So it's pointing up. Notice now, we're going to talk about this in a second. Notice that arrow is not equal in size to the mg arrow. I do believe that it's opposite in direction, but I don't believe that it's equal in magnitude. Why? Well, first of all, there's no reason to assume that it is. People get in the habit of thinking that, but I'm here to tell you, don't assume that just because you see a normal force that it's automatically equal to gravity. There's no law that says that just because two forces are opposite in direction, they have to be equal in magnitude. You might say, wait, what about Newton's third law? I'm going to get to that in a moment. I'm going to list all the Newton's third law action-reaction pairs, and we're going to find in a moment that mg and n are not an action-reaction pair. Each one of them is an action that has its own reaction in some other diagram somewhere. So that's point number one. Point number two, why do I think the normal is smaller than mg? Because I'm looking at my diagram and I see that there's another thing pulling. There's only one thing pulling down on the block, the weight of the block of the box. But there seem to be two things that are at least somewhat pulling up on it, or pushing up on it. The normal is pushing up, and the P, sorry, I did that again. Thank you, Tobias. Thank you, all you guys. Sorry, that's supposed to be a T. Sorry. The T is pulling to the right, but somewhat, but up somewhat. So there's two things that are pulling up. Oh, there's one thing that's pushing up on the block and one thing that's pulling up on the block. They're both trying to send the block up. So together, I think they're trying to support the weight of the block. Neither of them is individually alone supporting the block. If the normal, well, you'll see as we finish the diagram, but if the normal force equaled the weight in magnitude, then with tension also being there, the block would fly up. But the block is not flying up or flying down. It's on the y-axis remaining stationary, while on the x-axis it accelerates to the right. So anyway, you'll see more of that in a moment. But I think the normal force up must be smaller than the weight down. Finally, and then we have tension going off and to the right. I think tension's a very big force. Why? Because we were told it was 200 newtons. It's a lot bigger than 30 newtons, which is the weight of the block. And then finally, there's some friction pushing to the left. I know there's friction between the block and the table because I was given a mu. And I know that there's a normal force between the table and the block. All right, or the box. So that's my pure free body diagram right there. There were 4 lines in the system schema. There's 4 arrows in the free body diagram. And before I go on and break up these arrows into components, what I'm going to do is pause and list all, as per the instructions, I'm going to list all the action-reaction pairs, all the Newton's third law consequences. I want to make it clear that there are 4 arrows in this diagram. Therefore, there are 4 actions, so to speak, occurring. There are 4 forces acting on the block. Therefore, the block is doing 4 things back to the world. 4 things are happening to the block, so the block is doing back 4 things. There should be 4 action-reaction pairs. What I want to really emphasize here is don't think that any 2 arrows within one diagram are themselves an action-reaction pair. Newton's third law says, I push you, you push me back. It does not say that if I am pushed to the east, I must also be pushed to the west. If it said that, nothing would ever accelerate. So what do I'm getting at? Here's the action-reaction pairs. First, that force of mg says that the Earth is pulling down on the block, on the box. That's an action. The reaction then is that box is pulling up on the Earth. Okay, so mg itself is a pair. Mg is a pair. The action is Earth pulls down on the box. The reaction is box pulls up on the Earth. Then tension is a pair. The string pulls up and to the right on the box. Therefore, the box pulls down and to the left on the string. Every force is its own tug of war. By the way, this is really clear if you look in the system schema. That's part of the point of that. Each one of those lines is just a connector between 2 objects. Each one of those lines shows a mutual symmetric interaction, which I'm just delineating here. So mg is an action and a reaction. The action's in our diagram. The reaction would be in some other diagram, a diagram of the Earth. Tension, the action is in our diagram. The reaction would be in some diagram of the string, which I haven't drawn. Normal force says table pushes up on the box. Therefore, the box pushes down on the table. That's the action-reaction pair of that. And finally, friction says that the table is pushing the box to the left. Therefore, the box must be pushing the table to the right. That's the 4 action-reaction pairs implied or stated by our pure free body diagram. Okay? I do that to make it clear that, for example, the normal up should not be equal to the mg down. And I want to make that clear because we're about to do the math. We're about to like substitute in and solve for the friction. So we're going to need the normal force. Do not assume that the normal force is equal to mg. Like it totally isn't. And this is trying to sort of make that clear. But anyway, okay. So now we go on to the next step. Now, the next step is 3. We break up those force vectors into components that lie along coordinate axes. Like the whole purpose of all these pictures and everything is to get a full description of all the forces so that we can apply F net equals ma and solve for A. But F net equals ma is a vector equation. It is true independently but simultaneously along each individual spatial axis. F net equals ma is true along the y-axis, while it is also true along the x-axis. So we want, ultimately, in order to do that, we want to see arrows that only lie along whatever we're calling the x-axis and the y-axis. So I've chosen my axes. I've got an x-axis, I've got a y-axis. Any arrow that's already along one of those is fine. But any arrow that is like a diagonal line, I'm going to break up into components that lie along the constituent axes. In other words, that tension is pulling up and to the right at this angle theta. What I want to realize is, and this goes back to like the boat in street, the free float problem in the exam, and it goes back to lab 3, that if you pull something up and to the right, you're really pulling it to the right while you independently yet simultaneously pull it up. So the t vector that's up and to the right, it can really be viewed as a sum, a tip to tail sum of a horizontal vector and a vertical vector. And from SOHCAHTOA, from trigonometry, if t is the hypotenuse, then the adjacent side, the side adjacent to the angle, the horizontal side, is t times cosine of the angle. This is SOHCAHTOA. And the vertical side is the side opposite the angle is t times the sine of the angle. Now, so I zoomed in. And if there were other forces in my picture that were off axes, I would zoom in on them as well individually, and I break them up into their constituent components. But there was only one here, so I zoomed in on it and I broke it up. Now, what's the purpose of breaking it up? Now that I zoomed in and broke it up, I'm going to go back and redraw my free body diagram once and for all. I'm going to draw my free body diagram now, no longer as a pure diagram, but as a component diagram. And I'm going to replace that diagonal off-axis vector with vector components that lie properly along the coordinate axes. So, and it's a replacement. I don't want to see that diagonal line anymore. I don't want to see these in addition, and often this is where people lose points on exams and stuff. Don't put these components into the diagram along with the diagonal line. That defeats the purpose. That double counts the force. What I want to see now is a diagram that looks like this. This diagram now has mg still pointing down like it always did. It has friction pointing to the left like it always did. It has the normal force pointing up like it always did. But now, instead of t flying off at an angle, it has t cosine theta pulling to the right along the x-axis, and it has t sine theta pulling up along the y-axis. You see, now I have a bunch of, so I've turned my diagram from 4 forces to 5. I now have 5, right? But these two, t sine theta and t cosine theta, are smaller numbers than t once was. We're saying to pull at 300 newtons at a 30-degree angle is really to pull at like 150 newtons this way, while pulling like 86 newtons or whatever this way. You're pulling somewhat that way, some portion of 300, and you're pulling somewhat that way, some portion of 300. So this is now my component diagram. All the diagrams that I drew and all the work I'm doing to this was to get to this point, because now I go to my final step and I can apply Newton's second law, F net equals ma, to this diagram. I couldn't apply F net equals ma until this point. Now I can apply it because it's a vector equation. I'm going to apply it. In other words, to say F net equals ma is really to say F net along the x-axis equals MA along the x-axis, while simultaneously but independently, F net along the y-axis equals M times A along the y-axis. That's what this vector equation means. So I'm going to do, and now I've got all the information on the y-axis and the x-axis. So I'm going to go to the x-axis first. I mean, I'm looking for the answer along the x-axis. So I'm literally just going to add up all the forces on the x-axis, like T cosine theta and F. Only I have a coordinate system now where I'm assuming up is positive, down is negative, while simultaneously but independently to the right is positive and to the left is negative. So anything that's going, so I'm going to say on the horizontal axis, I've got T cosine theta and F. Only I'm going to make F negative because it's pointing to the left. So I write down, I'm on the x-axis now. The sum of the x forces equals M times the x acceleration. So T cosine theta is pulling to the right minus F. I mean, it's really plus negative F is going to the left. T cosine theta minus F equals MAX. And MAX is what I'm solving for. That's what I'm ultimately, so we're almost there, folks. What I'm solving for is AX. What we're solving for. So T cosine theta minus F equals MAX. But what is F? The friction force was not given. F always is mu, the friction coefficient, times the normal force. So I substitute in, like, right? F equals mu times the normal. So I can say T cosine theta minus mu times the normal equals MAX. I'm almost done, right? I've got an equation now for MAX, and I've got most of the numbers to solve for AX. That's what I'm looking for. But I don't know the normal force. I have one equation, two unknowns. That's a problem. It seems like I'm stuck. In order to solve for that other unknown, N, presumably, don't I need another equation? Yes, I do. Where could I possibly get it? The other axis. I haven't looked at the y-axis yet. And in fact, the normal force is acting along the y-axis. So let me now independently but simultaneously apply F net equals MA to the y-axis in order to get the M. So I go to the y-axis. On the y-axis, I had T sine theta pointing up. I had normal force pointing up, so I'm adding them together. And I have mg as well, but mg is pointing down. So I give mg a minus sign. I'm just adding up all, see, all I'm doing is expanding out F net in F net equals MA. That's all we're ever doing, is we're solving F net equals MA, and all our work is going to expanding out the F net, writing out all the forces. But where are we getting them, and where are we getting the pluses and minus signs? From our picture. And we can only do one axis at a time. So we need to break our picture into constituent axes. That's what all these steps we're all doing. All right, so I have T sine theta plus N minus mg equals MA y. Like MA in the y direction. But now this goes back to like last week. Like ultimately, I'm solving for A sub x. I'm solving for A sub x. Here I'm looking at the y-axis to get the normal force. Can I get the normal force? Yes, because in the y-axis, I know the acceleration. In the y-axis, the acceleration is nothing. The box is not floating up, and it's not crashing through the table down. The box definitely is accelerating, but it's accelerating purely along the horizontal axis. So, and this is why we look at one axis at a time. In the vertical axis, there is no acceleration. A sub y equals 0. So I make that 0, and that makes that whole right side 0. So I can bring mg to the right side. I can add it to both sides. Now I have T sine theta plus N equals mg. And that statement right there, the statement T sine theta equals mg, that's what I was trying to say back when I was looking at my original picture, my original free body diagram. You've got the normal force of the table is pushing up on the block, on the box, but also the rope is pulling up on the box. The rope isn't pulling up with full 300 newtons. Like 300 newtons is what the rope is pulling at an angle. But to be pulling up and to the right means it's pulling somewhat up and somewhat over. In fact, yeah, it's pulling somewhat up while the table pushes up. So together, the rope and the table are together supporting the weight of this block. T sine theta plus normal equals mg. Therefore, the normal is not supporting the whole weight of the block. The normal equals mg minus T sine theta. It's whatever the weight of the block is minus whatever help the T sine theta, the vertical component of the tension in the string is giving, right? So notice, if you're really with me, and we're almost done, and you've been great. If you're with me, you see this statement in the middle of the page that says N equals mg minus T sine theta. Like, that's why I looked at the y-axis. That's what I needed. I needed some expression for the normal force to plug back in to the friction, right? But please notice, that's not a memorizer. Don't go away and memorize that normal force always equals mg minus T sine theta. It totally only equals that in this, and that's a fairly complicated thing for it to equal, but it equals that in this particular situation because of this particular situation. Sometimes the norm, if there were no rope, so the normal could equal whatever it equals. You have to look at the axis to find out what it equals. Here, normal equals mg minus T sine theta. So here I will sub in into the x equation. So now I have T cosine theta minus mu parentheses mg minus T sine theta all equals max, right? Well, we're actually at a skip. We're just about done, actually, and that's farther than I got with the other section, for whatever it's worth. Like, I actually think you could finish it from here, but all that needs to happen now is like literally plugging it, was dividing both sides by m and plugging in the numbers, and you'll have an answer for A. I'm even willing to do that. Let me just pause for a second. Yeah, I'm going to do that to make sure we're all on the same page and so that we can all get these points. We have 8 minutes. We might even go early too, which is crazy. That's never happened. But let me just, can I just get it? If I plug in the numbers now in 1 second and get an answer, are we all clear what's going on so far? Like, are you with, is there any question to this point about the physics or anything? Or, okay, so yeah, okay, cool. Thank you, Gian. That's what so you're okay if I plug in the numbers now? We're good. We understand what's going on. Like, I mean, Gian, like, thank you, Gianna. Should we just go with what Gianna's saying? All right, I'm going to go with what Gianna's saying. All right, so I'm just going to recopy the next page. I think this, yeah. Okay. So I'm going to divide both sides by m. Now I'm going to plug in the numbers. Now, obviously, so now I'm going to plug in the numbers. Let me just move this over. Just moving it over. So. Wait, I think mu was 0.3. Wait, is that true? Sorry, I'm pretty sure. Sorry, I should. Yeah. Okay. Oh my God, what just happened? No. Oh my God. Okay. Okay. We will definitely get this answer, but we will not go early, but we will get this answer. Okay. You checked the, you, are we still there? I believe that's the answer. You could check the computation. I did it a little bit fast, but I believe the 0.3 divided by 3 is 0.1. 0.1 times 230 is 23. Yeah, I'm pretty confident of that. All right, that's the answer. That's how you do the problem. I would like, if you can present that nicely and show that you understand it and go step by step and doing your handwriting and do it like as a practice for the final exam, like there it is. So you don't have to invent the wheel, but if you could do it by next week, by midnight, that's 8 points on your exam. I think that will help a lot of people. I hope this, again, some of you still have to get your exam. I still have to get your exam back to some of you. I really apologize about that. They're coming, I promise. And I'm open for consultation or discussion at any time on any of the documents. So text me or email me and we'll talk. But, and okay, I'm sorry. And so I root for you all. I love you all. I'm good if you're good. I'll hang out for a second if there's any questions, but that's it. But have a nice weekend. Thank you. Have a great day. Okay. Have a great weekend. Thank you. Thank you. Thank you. Okay, I'm turning it off.